A very good morning to one and all. I welcome you all for session number 30. In this session, we will see how equation of a simple pendulum motion can be derived using Lagrangian equation. In the last class, we derived just by knowing kinetic energy and potential energy and using Lagrangian equation, we arrived Newton's second law of motion, which is given by F is equal to mr double dot. In this session, the objective is to understand how kinetic energy and potential energy of a constrained motion can be derived for a simple pendulum and application of Lagrangian equation to a simple pendulum. By the end of this session, you will be able to understand how you can solve Lagrangian equation for simple pendulum. Simple pendulum. A body of mass m attached to a length of wire L and it is suspended from its main position, and this is known as simple pendulum. Let us consider a body of mass m, that is Bob, is attached to a length L, is fixed within a rigid support and it is suspended from its mean position. On giving a small displacement, that is from mean position to the extreme position, and allow the body to oscillate. Now, we already seen for a simple pendulum, plane polar coordinate system is very suitable. If L, theta be the plane polar coordinates and if L is a fixed, which is a constant, then theta would be sufficient to describe the motion of a simple pendulum. So to derive the equation of a motion for simple pendulum, I need to know kinetic energy as well as potential energy. The kinetic energy is given by half m L square theta dot square. The potential energy is mgh, where h is equal to L minus L cos theta. So the potential energy V is equal to mgl into 1 minus cos theta. Now I know kinetic energy as well as potential energy. I know Lagrangian equation, Lagrangian function is L is equal to T minus V. Substituting T and V, then the Lagrangian term becomes L is equal to half m L square theta dot square minus mgl into 1 minus cos theta. Now all I need to do is differentiate this L term with respect to theta dot and with respect to now differentiating L term with respect to theta dot, that gives you ml square theta dot. Likewise, differentiating L with respect to theta dot, it will give you minus mgl sine theta, because differentiation of cos is minus sine. Now substituting these two terms in Lagrangian equation, that is dy dt of dou L by dou theta dot minus dou L by dou theta is equal to 0. Here qi or qi dot is theta. So substituting for dou L by dou theta is ml square theta dot. I will arrive at ml square theta double dot plus mgl sine theta. Taking m outside and rearranging terms will give you theta double dot plus g by L sine theta is equal to 0. This is the required equation of motion for simple pendulum. However, note that if the amplitude of the motion is very small enough, then sine theta is approximately equal to theta. Then the above equation can be rewritten as theta double dot plus g by L into theta is equal to 0. This equation is for very small amplitude. This is a general equation of motion for simple pendulum. Now you see that by knowing kinetic energy and potential energy of the simple pendulum, you are able to arrive the equation of motion for simple pendulum. So in this session, we learned how to derive its kinetic energy and potential energy for a constrained motion. And we also seen how simple pendulum equation of motion is arrived using Lagrangian equations. Now let's have a small MCQ session. Simple pendulum attached to a rigid support is an example of, since it is attached to a rigid support, so the option is A, holonomic. Question number 2. The coordinate chosen as a generalized coordinate in simple pendulum is, option C, is theta. Question number 3. Kinetic energy in a simple pendulum motion is of m L square theta dot L square L dot square. Do remember, if the length is fixed, L dots will be equal to 0. So the option is none of the above. Potential energy in a simple pendulum is given by, you know that we have seen, mgl into 1 minus cos theta. So the option is B. Question number 5. Lagrangian equation of a simple pendulum motion is given by, it is of m L square theta dot square plus mgl into 1 minus cos theta. So the option is D. dl by d theta, that is differentiation of L with respect to theta from Lagrangian for a simple pendulum is, it is minus mgl sine theta. Question number 7. Lagrangian equation for a simple pendulum is theta double dot plus g by L sine theta is equal to 0. This is a general expression. For a small amplitude, sine theta should be replaced with theta. Question number 8. For small amplitude of a simple pendulum motion, sine theta is approximately equal to this. It is equal to theta. So option is answer C. For small amplitude of simple pendulum motion, Lagrangian equation of a motion is, in general equation you need to replace sine theta by theta. So the option is C. For simple pendulum has a variable length, then L dot square doesn't become 0. So which means your expression should be of m r dot square plus r square theta minus mgl or mgr into 1 minus cos theta. So the option is answer D. So in this session we have seen one more application how Lagrangian equations can be used to derive equation of motion for simple pendulum. Hope you enjoyed this session. Thank you all.